All right, thank you, Leanne. Thanks, everyone. Let me, sorry, adjust here. Sorry about that. All right, so I wanted to give an overview here of image differencing in science pipelines. My name is Bellm. I'm at the University of Washington and work for the Rubin Observatory as the alert production science lead for data management. And of course, I want to emphasize just at the beginning here that this is the work of many people over a long period of time. I'm presenting the results, but and really sort of only representing their work. So this is just a partial list of folks who have contributed to algorithm development, QA, pipeline development, specifically for difference imaging, but obviously all aspects of the science pipelines are contributing to the work here. So Jean just gave a really nice overview of image abstraction algorithms. So this will be a little bit of a repetition. So I will be a little more brief. Again, the idea with image subtraction is that you have some new science image that you'd like to compare to a template, which is probably, but doesn't have to be, a coad of previous exposures. And that if you difference them in some sense, you can find the things that have changed from one to the other. The advantages to doing this is that, as you can see of this discovery image of a supernovae in a nearby galaxy, you're removing a lot of the sort of nebulosity and galaxy light. It also sort of simplifies source association, and it's also useful in crowded fields where there may be many stars close together, and you can remove the ones that are not varying and identify the things that are. And again, historically, a lot of image differencing development is coming out of things like microlensing surveys, where you're looking at very dense fields. It's also, a little more simple than sort of doing a first principles forward model of the entire, of everything in the image itself. And again, a lot of these surveys using image differencing are in the time domain. They're interested in finding things that are changing and triggering follow-up on relatively rapid timescales. The challenge, of course, from the ground is that the image quality and the PSF are varying from image to image, so you can't simply just do a pixel difference or something like that. So as Jean described, some of the early work was using ratios of PSFs in Fourier space to convolve the new image to match that of the template. And of course, this requires that you know those PSFs relatively well, which can be challenging in crowded fields. And there are various kinds of numerical difficulties that can make this somewhat unstable. So then, of course, Alard Lupton in 1998 suggested that instead we model that convolution kernel as a sum of a set of basis functions, which can be complete, although typically people are using a truncated subset of that. And then you can use least squares to solve for the coefficients of the basis functions. This is optimal in the background dominated regime if there's no noise in the template, or you can neglect it. So this works pretty well. And again, there's some other nice features. You can allow for spatial variation in the PSF across the field, do background matching and things like that. So then a few years ago, Zackay, Ofek, and Gal-Yam pointed out that, again, if you're trying to measure point sources in that background dominated regime and there's noise in both images, Alard Lupton is not optimal. And so they proposed what we often call today the ZOGY algorithm after their initials to identify, to solve for that difference in Fourier space. A nice feature here is it's fully symmetric between the science and template images, although again, it requires knowledge of the PSFs or the ratio more accurately. And so that again can be challenging in crowded fields. So then Robert and David Rees, who was with the project at the time, wrote up sort of an extension of ZOGY that showed how you could apply the same ideas within the Alard Lupton framework. So continuing to use basis functions to derive the convolution kernel. And then you get those optimality guarantees even if there is noise in the background images. And you're also getting that noise whitening property. So It's the same expression, just whether you're using a basis function expansion of the kernel or the ratio of the PSFs. And so in this framework, then you don't need to know the PSFs directly, and we see in both simulated and real data that you're removing a lot of the noise covariance as you'd expect. So this is the algorithm where we focus most of our attention in the subsequent years. We do have all of these implemented in the science pipelines today. So the classical Alard Lupton with both pixel basis and some of Gaussian's kernels. We have an implementation of ZOGY, which also includes an extension that uses piecewise constant spatial segmentation so that you can allow the PSF to vary, as well as what we're calling decorrelated Alard Lupton. I will say that until very recently, both of the ZOGY and decorrelated Alard Lupton implementations in the stack had bugs in their discrete Fourier transform implementations. We had identified that a few months ago, and the fix is in place, and so I'm showing results with that fixed, and it'll be on master relatively soon. So, so I want to acknowledge that. Again, Jean described a lot of the other issues that we have to pay attention to in order to get good difference images. You know, having the right algorithm is obviously important, but it's not the whole story. We need good templates. Jim described yesterday sort of the wide variety of coads flavors that the DM stack can produce. And so I think that the message here is that, you know, we're in the process of investigating the performance impacts of various choices. So when you think about what images even are included in that stack, there's sort of various trade-offs in terms of how many you include. You know, more images improves your signal to noise, but may sort of include a wider seeing range. You need a sort of a certain number to be able to effectively reject asteroids. There's also a little sensitivity around temporal range. Again, you don't want to have high proper motion stars sort of showing up if you coad over too long of a range, but we do need enough images, we think, to model DCR effects. And so that's a trade-off that we're still exploring. Similarly, we have to worry about discontinuities in the PSF. You could imagine using PSF match coads to do that. Or some form of careful bookkeeping where you know where the boundaries are. And finally, you can do coads that are direct PSF matched or Kaiser decorrelated coads. In the first year of the Rubin Observatory LSST survey, we won't have all sky templates produced by data releases. Those will be generated in DR1. And so we're still sort of discussing what our options are for doing alert production in the first year of the LSST survey. There's a tech note, DMTN 107, that describes a range of options that are under review. In particular, it's likely that we'll use templates that have been built from any commissioning data that's available. That almost certainly won't cover the whole sky, but will get us a head start. And then we're looking at the possibilities for doing incremental template generation in the first year outside of a data release. So stay tuned on that. Again, everyone has their own rogues gallery. I come from PTF and ZTF, so this is a set from the PTF survey of all the various kinds of ISR and artifacts and calibration issues that can produce false positives, bad astrometry, you know, halos, glints, streaks, masking problems, all of these things. So this is just, I think, making the point again that we have to care and pay attention to all stages of the pipeline in order to get good difference performance. All right, let me move on and discuss a little bit what we have today and show some results on precursor data. This is just emphasizing that we run difference imaging both in real time from alert production as well as annually in the data release production. My team focuses mainly on the nightly alert production, which is driven by that high level requirement that 60 seconds after the camera reads out on the mountain, we have to send out alerts on everything that's changed to the community brokers. And so we're sharply time constrained in how our pipelines can run. DRP doesn't have that same constraint, and so can in principle do different things in difference imaging. We are using the same algorithmic building blocks, and so can feedback information from one to the other. But you know, there can be some subtleties in how difference imaging is run between the two. In particular, source association will be quite different in DRP and in alert production. To test today, we're using a variety of precursor data sets, mainly from dark energy camera and from Hyper Supreme Cam. Sort of our workhorse day-to-day data set is the HITS data set from DECAM, which is, we're using 3 of the fields that are observed over a couple of different seasons. They're in G-band, and we have a week's worth of observations, 4 or 5 visits a night. And you can see on the right side of the screen there, density plot of detected objects in that data set. We also have recently started differencing the ultra-deep HSC field Cosmos, which is multi-band and has a large number of visits. HSC has an ADC, so it doesn't have any DCR effects. We are going to need to move into testing in crowded fields. There are some good, both HSC and DECAM bulge data sets that will be useful for crowded field analysis. We expect to start looking at those later this year. And in terms of looking at sort of a large, well-calibrated data set, the DES supernova fields are particularly attractive for their long baseline, multiband, and so on. One constraint I would say with all of these precursor data sets is they're relatively small dithers relative to what we expect from the LSST survey, and they don't have the big field rotation. We will be a little bit under-tested in that regime, I think, until commissioning. So that's something we have to pay attention to. We have a nightly continuous integration process that runs on a small subset of right now the HITS and soon Cosmos that just gives us some very high-level metrics to let us look for performance changes as we update the code base. And so we pay attention to this as a way to just make sure that there aren't things coming into the pipelines that are giving us large performance swings that we don't understand. On a monthly timescale, we process larger data sets. Again, mostly right now that's HITS, but that's expanding. This is a zoom in on a subset of chips from that field. On the left is just the raw detections out of, you know, with no filtering at all. And on the right is with some simple filters on some basic pixel flags. Each point here is one object, and the scale is by the number of detections. And so you can get a sense of, you know, repeat detections versus sort of one-off detections. We have some high-level requirements on completeness and purity, and these are at signal to noise of 6. For transient science, we have to achieve 95% purity and 90% completeness. And for solar system processing, we bump up the completeness to 99%, but allow the purity to drop to 50%. And so along with the 60-second latency requirement, these are really the driving requirements that my team is focused on. Part of the verification of this involves basically building a machine learning algorithm on top of that, something like real bogus. And we also expect, as was discussed in the previous talk, that you can use that training process to help us improve the pipeline by looking for various clusters of failures and boguses. This is all relatively new, so this is recent testing. So we started some initial injection of fake point sources, and so that lets us assess completeness. So this is, again, injections of point sources into the HITS science images from about 19 to 24th magnitudes. Again, the 90% completeness is the relevant requirement. And you can see that we're on this data set exceeding that relatively comfortably. And so that's a good sign that we're detecting the sources that we should be. For purity, I believe, and I others have other ideas, I'm happy to hear them, but I think really putting eyes on the data is the best way to see what the contamination is. So we dumped out several thousand difference image source detections and classified them through a Zooniverse project in preparation for this talk. And so this is, again, this raw detection plot with the major classes. I've boxed the sort of clean point source class, and you can see some of the other categories there as well. I'll show some cutouts in a moment. If we filter that, apologies, the colors change here. Again, I've boxed the clean point sources. This is if we just filter on a couple of coarse flags. This cuts the completeness just a little bit. The number of clean point sources drops just a smidge, but not a great deal. And so you can see a little more clearly some of the dominant effects are from dipoles, or still some edges and some non-detections, which I'll discuss in a moment. So just showing some examples, these are some cutouts of clean detections. Again, for LSST, we care about both positive and negative detections because we care about variable stars. So we want to detect both of those equally well. So we have lots of good detections. We do see a number of detections on saturated bleed columns that have been interpolated over. So that's an area where we can work on our flagging a little bit and make sure that we're handling that as well as we can. There are plenty of dipoles, so that suggests our astrometric solutions are not as good as they could be. Recall again that this is for alert production, so we're not talking about using some of the, all of the machinery that DRP can do for really accurate astrometry. We have to sort of do as well as we can in that 60 seconds. And so clearly we have some more work to do with that process. We have some ideas. There are deconvolution artifacts, problems with the kernel solution. We know the sort of flow chart of comparing how the different science and template images, how their PSFs match up are not as good as they could be. So this is something that obviously needs some attention. And then there's a surprising number of detections where you look at the cutout and you say there's nothing there. So you can sort of see some maybe interpolation or background shifts in these cutouts. So this is something where we need to dig in and look and see if the variance planes are misscaled or something like that, and get rid of these. So let's then ask, how does our sort of raw detection rate that I just showed compare to other surveys? Jean just described for pan-stars a very high rate. I pulled from this 2013 paper, a raw artifact to non-artifact ratio of sort of 10 or 50 to 1. DES year 1 reported 13 to 1 before machine learning was applied. And in ZTF, depending on what exactly you say, is obviously an artifact. It's somewhere between 2.5 and 25 to 1. So the results I just showed, again, running decorrelated and Alard Lupton on hits with no filtering at all. That's a raw to artifact to non-artifact rate of about 4 to 1. And with the coarse filtering, it gets down to about 3 to 1. So we're doing quite well, actually, relative to other surveys with the science pipelines as they exist today. This is all before machine learning. We expect and will need to provide machine learning scores so users can apply their own completeness purity trade-off by adjusting that threshold. And this slide is just to emphasize that the state of the art today for machine learning classifiers is quite good. This is one example using deep learning from ZTF, the Barai classifier by Dima Duev. And they're achieving, again, on that ZTF input, 98.9% completeness and 97.6% purity, which would exceed our requirements. And that's at 5 sigma, I should emphasize. So that's a very good sign that when we do start to build something like this, we'll be able to meet our requirements. So where do we go from here? Obviously, there's plenty of refinement still to do on precursor data, and then obviously when commissioning starts, we'll be digging in detail. So ongoing performance tuning and QA. As I said, we want to add additional precursor data sets on crowded fields, some larger scale runs. There's likely some interesting work to do in conjunction with DESC around the DC2 simulations. There are some opportunities to dig in on difference image kernels. I know Robert has some interesting ideas there. I showed completeness from fake insertion. That was very much a duct tape and baling wire process. We need to make that production scale so we can run it all the time. There are some aspects of solar system science where we need to do some work. We need to do trailed source fitting, as well as attribution of already known solar system objects, so we can label those appropriately. And finally, start developing the infrastructure to train and keep up to date a machine learning classifier. So this is my summary slide. Image differencing is a big part of our pipelines, and we are continuing to work on algorithms and their performance tuning. This is a process that really cares about everything in the pipelines, and so we have to take care everywhere. The good news is we have very flexible pipelines with lots of implementation choices of all the major algorithms, and so we're going to continue to refine those with precursor surveys to prepare for the full survey. The early results, I would say, that I'm showing today are pretty promising in terms of meeting requirements, although I think it's worth adding the clear caveat that the hit state in particular is not representative of the full LSST survey, particularly in terms of dithering, but in its other characteristics as well. So stay tuned. So thanks very much, and happy to take questions.
Thank you, Eric. We have a round of applause for Eric on Slack. I'm not seeing any hands up. Do we have any questions for Eric? Michael, you have a question. Just a second.
Sure. I actually had a different question than what I wrote, but I think my question really is, what specific object scores do you think will be most interesting? Jean talked about dipole scores and implicitly some related stuff. What per source scores are you planning to investigate?
I'm not sure what you mean by score in this context, Michael.
Moments, what happens if you use increasing annuli? Does the flux continue to increase? Things that you can calculate based on the pixels, not necessarily model fits.
So you're thinking in terms of assessing real bogus or something like that?
Yes, I mean, yes, I wouldn't phrase it that way, but sure.
I'm concerned I'm still misunderstanding you. My thinking on the real bogus problem specifically is that you try not to think hard about the features at this point. It's pretty clear that the neural nets are far and away more performant than any sort of hand-tuned feature set, and so from that perspective, I don't think I don't think the answer to your question is very interesting, but I don't think that's actually your question. I think you're asking about algorithm tuning specifically.
I think I'm talking about feedback for algorithm tuning that can be informed. I think we philosophically disagree that, all the surveys I've been part on, we have a set of 20 different scores for each thing, and we look at thresholds and stuff for tuning that. That's been useful and informative, and you can loosely reason about those. I do also agree that clearly this issue of residuals you don't have a good model for is a good thing that's handled by CNNs and the like. But no one's actually done that. Well, no one's the wrong word. When Jean talked about that a little bit. But certainly until very recently, people weren't doing that. And I guess the theme is I'd really love to go back and improve the algorithms, as you were saying.
Yeah, I think that's right. And let me return to your larger point. Yes, I do think there are things we can keep an eye on as we dig in here. Again, the dipoles are an obvious case where we already pledged to deliver, but we'll have point source and dipole fits to all our different sources. And so assessing the relative quality of those two is an easy way to look for trouble in the astrometry. I think this is potentially an area where, you know, useful experience from precursor surveys is helpful, right? You know, if there are 12 things that you're tracking, I'd be very interested to hear what those are, you know, as we dig in.
Bruno?
Yeah, yes, hi, can you listen to me?
Yes.
Yep.
So yeah, my question was quite aligned to what Michael was asking. I think it's related to how are you assessing the tuning of the configuration of the algorithms? Are you looking at the covariance of pixels? How are you doing this? Or you have a preset of configurations that you somehow figure out are best suited for SST?
Yeah, you know, I think from my perspective, where we have been starting is has just been looking at effectively the high level numbers as a starting point, which is to say that, you know, most of the detections are false detections, although as you saw today, that ratio is somewhat lower than is commonly assumed, at least on this data set. And so, you know, using that as a guideline, if we sort of blow up our detections on individual images, that usually tells us we're stepping in the wrong direction. We're not yet, I would say, in a position where we are, I think, dialing in on the last, you know, 5 or 2% of sensitivity. We're still, I think, in the regime of making relatively coarse steps in this sort of algorithm and you know, configuration space, and so that's been sufficient to date.
Okay. Thank you.
Yep.
Keith.
So this could be a question either for either the two speakers. So how is the performance in terms of the accuracy, precision of the actual light curve measurements? So not only recognizing that there's a different image analysis source there, but the accurate recovery of the photometry, and also will this be tested primarily by a source injection or some other method?
Yeah, that's a great question. I can take a stab at that for LSST, and then if Gene wants to comment on the PS1 side, I don't remember off the top of my head what the relevant requirements are for AP. We do have, you know, very solid you know, photometric requirements in terms of our precision. Fake injection is a nice way to test that, and is relatively straightforward. So we would probably use that as our first pass, but we haven't started that work at all.
From my side, I think I don't have a great number for that answer, but I know that the supernova teams go back to force photometry to get a reliable light curve. I don't think it's great, but I think it can be okay for, I think some RO-Lyra tests showed that you could use it to reproduce light curves.
Thanks.
Okay, do we have any more questions? I'm not seeing any more hands up. Okay, so if we have no more questions, that brings us.
More from Michael, Leanne.
Oh, sorry. Michael, are you still unmuted or not? Probably not. There you go.
One last question was, you know, Robert was talking about how, right, Robert, sorry, in principle that you could reconstruct any individual image from the difference image, right? That's all the same information. Is that a thing that you're actually testing as a metric?
No, we're not. Although there's certainly some relevance in, you know, that, for example, the alert packets that we are preparing to send have just the difference in the template in them, right? And so with the assertion that you can recreate the science image from those, and so we should certainly be making sure that that's true before we ship those off.
Yeah, and I think that the full context is cases where what you are producing is nominally an image versus what you're producing is a source detection metric.
Yeah, that's
like
a good
the
point.
S for ZOGY. Yeah.
Hi, when you were showing the completeness plots based on hits, so these are essentially detections that you have relative to the numbers that hits themselves had, or how are you calculating completeness here?
Oh, these. Again, these are fake injections, so we know how many of those sources we put in. Yeah.
Okay. Thanks. Sorry.
Yep.
Okay, so I don't think we have any more questions. Okay, so with that, I'd like to thank all of our speakers today for their excellent talks. This brings us to the end of the day, of day 2.